Can you hear and see my screen?
Yes.
All right, wonderful. So hi, everybody. Today I'm going to talk about the work which has been done before in the SAI community regarding the telemetry. And this is, we have already done 2 iterations on this. We initially started with a very basic infrastructure, which provides ability to give data, and they were essentially sort of GET APIs. That was our very first iteration. So let me just go over the agenda, what I'll be talking about. So yeah, so I'll just do a recap of what we have done so far. Then I'll define what is the problem we are trying to solve in this iteration. And then just a little bit of an approach. And approach is what is expected from silicon to solve this problem. And then also how we are, what kind of use cases this will solve. And then there is a PR open, which enhances the existing TAM spec, the telemetry spec, and adds a bunch of new kind of attributes. So that can be seen in the GitHub. So that's the agenda for today's meeting. So again, just to recap, in the very first iteration, we had basic GET APIs where information was retrieved basically using a pull model. And in the second iteration, which we call as TAM version 2, we enhanced that and created a push model architecture where the data plane can send the data to an external collector or to a local collector. And local collector in this case could be a Sonic. And what we did, we kind of created a main framework, which was a very generalized framework, and things can be, different objects can be put together to achieve functionality. So using that, we solved the case of streaming telemetry, where the data is being pushed out by the silicon directly to the local collector or to the external collector. We also added a bunch of APIs and attributes to solve the in-band telemetry problem, and there were 3 variations which were supported, which are supported in the version 2. We support IFA, which is a Broadcom specific in-band telemetry, but it's present in IETF. P4INT, which is proposed by the Barefoot, now Intel, and IAM, which is a very purist approach towards in-band telemetry and is progressing in IETF. So that was part of the in-band telemetry. We also added ability to specify a register for the events and then subscribe for the events, and then those events can be published to the subscriber. Excuse me. And then we also added a framework for the mathematical functions. So you can specify to do the mean, mode kind of functions and advanced functions through the attributes. Flexible data coding was added, where the data can be streamed using various data decoration methods. And then, of course, the transport itself, where the transport can be TCP, UDP, could be a local host. And there is a specification for gRPC as well. I don't think we support it, but there is a specification for that. So this is all the work which we have done, and the implementation is present in various Sonic releases. So what we are doing, what we realized by doing that iteration, that suddenly there is a very high fidelity but very high volume of data which is appearing either to the collector or to the local NOS, right, to the local collector. And then what is doing that ability to ingest the data, process it, prune it, and then store it, that was costing enormous amount of money just to scale the collector subsystem. And then because this data is coming to the collector, it's being processed, and there is a delay in all that processing overhead, then the root cause analysis, if we are really looking for a real-time analysis and the feedback in the system, that was getting delayed. So there was a delay in the root cause analysis. That was becoming an issue. And then also when the event happens, when there's a trigger which a collector or a local subsystem receives, and it wants something in the history in the past to correlate, that's not present in the data itself. So that becomes a responsibility of the collector to store all that data and use the history if it needs to. And again, that causes the scaling problem. And what all it was doing, that as the SLAs are increasing, like there are now 5 nines, we talk about 6 nines, the tight SLAs. So ability to satisfy these tight SLAs was becoming harder and harder. So that's sort of a domain of the problem definition, which we are trying to solve here. And in this iteration, what we have done, we have taken a bunch of use cases and then try to solve them with various methods. So that's what remaining discussion I'll be focusing on. So our approach is that we should be able to provide methods to do some pre-processing of the data. And pre-processing, as I talked, can be a simple mathematical functions. We should also provide some APIs or the attributes to provide some state maintenance. And state maintenance is not done in the software, it's done in the hardware. And the state maintenance at the minimum could be, we can think of that, what's the residence time? What is the average residence time a flow is experiencing? Is there a path change for a given flow? Meaning that this flow earlier was experiencing a path from input 1 to output 2, and it has changed from input 1 to output 3, okay, or so and so forth. So if there's a path change, meaning that it has to store some previous information, right? And then same on the drops. Is it the drop for a flow which is experienced for the very first time in a given time interval? Or for a given time interval, it's not seeing any drops, so the last drop observed became a last drop event or last drop seen. So those are the states which I'll be talking about. And all this, these methods, we still focus at a flow granularity. So there is a value of doing this at a minimally at a flow granularity because it scales well. If we do everything at a switch level, then mapping of that information to the flow becomes the job of the collector, which we are trying to solve. And then also we can, at least for the well-known ports, we can map these flows to an application. So that's the approach which we are taking to solve this problem. So again, pre-processing of the data, wherever it's possible, some state maintenance in the hardware, and that depends on the capability of the silicon. And all this processing is maintained at a flow level, right? So that's our approach. So this is the very first one I'll be talking. This is the first use case which is of interest. So today we have mechanics to capture the drops. Okay, so those mechanics exist in the SAI specification. Those mechanics exist in the TAM specification and also in the hardware. We are saying that, what if, take an example, there is a flow which is experiencing drop. What if we are, as in the SAI, okay, with the help of the hardware, is able to give an event which only it says that for a given flow, this is the drop reason which I am seeing, hardware is seeing, and essentially generates an event which is a drop start. Okay, so if you see a dashboard at a Sonic or at any management console where the flow is being mapped on the dashboard, then you will see essentially an event which says, okay, for this flow, now the drop start has happened. Along with the drop start, you will get some metadata, and metadata can be, what is the drop reason, what is the incoming port, what is the outgoing port, what is the timestamp when the packet was dropped, what is the QID, okay? Is this since this is the very first drop, so drop count will be 1, of course, but this is the minimal set of data we think that is useful to make meaning by the collector subsystem. Now, what can happen that this flow, which has experienced the drop at the very first time, may continue to see the drops, and the drop may be the same drop. So if there is a same drop, then typically we do not want to generate the same event, right? But the counter will keep on incrementing. So if the collector sees that, oh, there is a first drop, and then there's a new information coming in from the hardware, then it says, okay, drop season is same, but I'm seeing same drops happening. So it said, okay, drop is still active. That's one possibility. Other possibility is on the same flow, you may also see another new drop reason, right? So in that case, a new event will be generated, which will say that this flow is seeing a new drop. And along with that, you will again get all this set of information, right? And then subsequently, eventually, corrective actions will be taken, system will stabilize, and then traffic will come back to the natural level, and there will be no drops. So this window, drop stop, essentially is monitoring time window, which is specified by the operator. So in this window, essentially, you see a state, which is a drop start. Drops are active, and then eventually drop stops. So if we are able to provide this kind of mechanism in the SAI, then the collector now scales very well. Instead of receiving thousands and thousands of drops, even for the same reason, now all collector gets is a single event, which says, okay, the drop has started, and along with the drop reason, if the same drop reason is seen, then it does not send any event. Simple indicator is a drop count. Okay, if there's a new drop, then another new event comes in. Okay, if there's nothing, then nothing comes in. And eventually the drop aging window will expire. And if there are no drop season within this time period, then essentially your drop stops. Okay, and then everything looks green again. So, so this is an interesting use case. And what we observe that for a given deployment, that if we do this intelligent drop monitoring, which we call as a stateful drop monitoring, then the traffic load for the drop packet reduces by almost 90%. There's still some traffic which need to be handled by the collector. And it's like if the drops are active, then do you want a push model or a pull model? That creates interesting profile of the traffic. But essentially, now cost of processing this traffic goes down by 90%, and that's a pretty huge number. So this is one interesting use case which we are trying to address in the SAI specification. This is just again the state machine. This is the FSM for the drops. Essentially, system will start in a good state, okay, where nothing is happening, and then the first event it will see is the drop start, okay, and then what we call as FSP is the first seen packet, and the system will transition into the drop active, okay, and then there's a tick coming, which is your edger tick, and if during that tick the drop is inactive, then you stays in this state, and then eventually when the end ticks expire, you say the drop has stopped. So event which is generated is a drop start and drop stop, okay, and this is for single drop reason, and same FSM is going to run for multiple drop reasons. So that's just a depiction of that. So much of processing has happened, which earlier collector is doing, now is being subsumed in the hardware, and SAI will provide ability to take in this summarized data and expose it to the collector. So that's on the stateful drop monitoring. And then next use case, which I'll be talking, is the latency monitoring. Now, we already have attributes for latency monitoring, but they are sort of static in nature. When I say static in nature, that what we can do, we can say that there is a high watermark or a low watermark, and then there's a strict comparison between at a high watermark or a low watermark, and then event can be generated, right? Or you can say that latency, if it exceeds certain value, so the residence time, and we are talking about the switch residence time. We are not talking about the end-to-end latency. This is at a switch level. So if the residence time exceeds certain value, then we are saying we generate events. So that already exists. But again, this is not very intelligent in the sense that you will get false positive if there's a jitter in the system. There are spikes, which are really not a breach, which is not of interest. we will see those, we as in the collector will see those events appearing, and then we'll treat them as a failed events. What this use case is saying, that introduce a hysteresis cycle, meaning that when the breach happens, you treat it as a fair breach, that, okay, there is a breach, high watermark breach event happen. Now after this, if there is a jitter and there are multiple such variations are happening, there is really no need to generate this event at this point of time, okay? Only when the system goes through a transition where the low breach happens, which is my normal operating window for the residence time, the hardware is going to generate a low breach event, okay? And then the system is primed again to generate any high watermark breach event, okay? And essentially what it does, if you see, it has a dampening effect on these transitions through the high watermark and also transitions through the low watermark. And this goes back to the point I was talking about earlier. Now, what we have done some intelligent processing, and then instead of generating this high volume of data, right, although it may appear as low volume here, but still all these transitions which are happening at a nanosecond boundary or a microsecond boundary will appear to the collector. So we are dampening all these transitions, both at the high level and the low level, and then generating only when the true transition happens at a high and to a low, and to high and to a low, and so on and so on. Right. So in this case, if you see, again, there is some notion of history. We have to maintain some notion of historical data, that to suppress this event, we need to know that, okay, there is no low watermark. The system is not yet primed. Previously, what I have seen is a high watermark. Similarly, to suppress the low watermark, the system has to know that this transition is not happening from high watermark, but is happening from a low watermark. It's not of interest. So this is a historical data. This is a historical data. This is a historical data. And this needs to be stored somewhere in the silicon. Again, it needs some capability from the silicon, but what we are trying to do is provide APIs in SAI and attributes where such systems can be configured and data can be provided to the collector in an efficient manner. So that's the latency monitoring. And this is the PR. You can go, and there are more use cases. I'm kind of stopping at these only two interesting use cases. As I said, there are path change, and there are other use cases which can be addressed by this framework. You can go to the PR and you will see it's a fairly reasonably large diff, but it does not introduce a new set of APIs. It essentially introduces a new set of objects. I think there are objects. I'm not sure. Definitely new attributes. It has added new ACL actions and a lot of new attributes within the time specification. So SAI tam.h, if you go and see, there are probably a lot more drop reasons and latency monitoring attributes have been added. This PR will go in discussion probably after the OCP. We deliberately kept this PR on hold because there is quite a bit of interest on this topic, and we really want to make sure all use cases and all silicon implementations are kind of handled in a more comprehensive manner. So that's on the presentation, and I'll give 10 minutes for the Q&A. So if there are any questions. Okay, if there are no questions, then 20 minutes was the slot for this presentation. Then we can give 10 minutes back to the community.
Hey, Jai, this is Omar. Maybe let's just wait a little bit just to make, I think there's a little bit of delay on the FN Tech, presentation on the app. And then as people watch that, they can then join in. I think that's how that works. they can join in, and then when they join in, they'll join in to ask a question on the Zoom. Also, maybe we can double check on the in the session right now. 1 second. We can check in on the Zoom session if there are questions here, on the FNTech app if there are questions here. So let me see. So I'm just going to review the discussion here. I don't see any questions there quite yet.
Yeah, I don't see any question on the chat window.
Okay. So Shin, am I understanding that right? In terms of folks, if they wanted to speak and ask a question, they would click on that button in the app.
Right. Yeah. Otherwise, they just post the questions on the chat window.
Okay. I think it's probably the time's gone there. So, all right.
I can show the meanwhile PR what work is being done. Okay, so this is the PR. Let's see, files. It has, so this is the specification, which is talking about what kind of errors.
Jai, we still see just your PowerPoint screen.
Oh, sorry, my apologies. Okay, how about now?
Yes, we see this now, your browser screen with the side advanced telemetry GitHub page.
Right. So this is the PR, and what I'm showing is the diffs on the PR. So there is a new document which is added, and this document goes quite a bit in detail that what kind of packet drops we are considering, and then what kind of modes we can have. So today what we have, we kind of refer it now as a stateless drop monitoring, meaning this is like a dumb drop monitoring. Any drop happens, that information can be mirrored to the collector. Then there's a variation which is introduced, which is one level upping it, that instead of just monitoring any and every drop, you can specify that I'm only interested in all the drops or specific drops for a given flow. So that's what we call as a per flow. And then you can go and make it even more intelligent, and you say, I don't want duplicate drop reasons for the same flow if they're happening repeatedly. So essentially what this does, it does a deduplication and then reduces the load on the collector. So this section will go in detail. And then this is some of the architectural goals which I wanted to highlight. And all it does, it gives a clear idea that what's the expectation from the NOS if it's trying to define such rules, that what's the good practices. And then this section goes in the specification update. So there are new kind of actions which are added. ACL entry has been updated, and then extended TAM events, event type has been updated. There is, and also, so this is quite a bit. And then same thing on the stateless drop monitoring. The examples are there. And I think the more interesting thing is that sometimes, not all the time, we want all this information to be in a push model. Sometimes there is, we just want a callback. It's still a push, but we want a callback. So there are examples I have put in this that if the host wants to do a processing using callback, then how the registration can be done for these events. And it's pretty neat. This probably, I'm gonna extend it further. I'll take one big example and then capture it. So that was on the stateless, and then basic mechanics of callbacks works for everything. So this is policy based, where you can define a policy for monitoring the drops for a given flow, and that becomes flow-based stateless. So it is still not very smart, but one level smart, where you can define the intelligence at a flow level, then defines the steps to create it. And then this is the really smart drop monitoring, where the complete deduplication of the information happens, and then how that need to be done. So that's, and this is the flow latency monitoring, that same thing. What kind of latency we are measuring? So first we define the definition of latency for a typical pipeline. So this is the SAI logical pipeline, where the latency is a function of ingress pipeline, MMU fabric, and the egress pipeline. And then what we are not trying to just monitor only part of it. So residence time is treated as summation of all three. And then there's a workflow, what update we are doing in the SAI. And you see mostly these are attributes. Then there are different action types and transports and so on and so forth. So it's fairly big. And this is the intelligent with a high and low watermark. So yeah, so it's a fairly big spec, and I expect it to be grow a little bit bigger than this. I'm going to add some more examples. So I think that's pretty much I have for today.
Great. Thanks a lot for actually, you can see there's a lot of detail in on GitHub there in terms of the write-up, and for giving us an overview.
Yeah, thank you.